Good morning, everyone. It's a pleasure for me present here, Javiera Barrera. He's associate professor from the University Adolfo Ibáñez, and she has a PhD from the Universidad de Chile with a passion in Paris, UFR Mathématiques Informatique, Université Paris Descartes, I think. I don't speak French, obviously. And she's gonna talk about the role of multivariate Marshall-Olkin model in network reliability and some contribution. Javiera, welcome. Thank you for being here with us.
Thank you very much, Alejandra. Muito obrigado de ser recibida en Brasil, en un país que yo amo de todo corazón. Okay, so I will talk about the role of multivariate Marshall-Olkin model in network reliability and some contributions I and my colleagues have done. If somebody has any question, can put it in Spanish, English, and slow Portuguese. I could try to understand. Okay. I will talk about what are geographically correlated failures, because this is a motivation to use the Marshall-Olkin multivariate model. I will talk a little bit of network reliability to explain how do we compute and what do we want to capture in a network. And then I will go to explain what is the Marshall-Olkin multivariate model. Afterwards, I will present a subfamily of the Marshall-Olkin called the Levy-Fraulty Marshall-Olkin, and a result we obtain in an extreme value theorem, and also a proposition to simulate this Levy-Fraulty Marshall-Olkin. And I will close with some conclusion and open questions that are interesting to keep understanding of this model. Geographically correlated failures are failures provoked in networks that are displayed in a geographical zone, like the one we see. This is an electrical network that we see in the right-hand side of the slide. And these networks has elements. In this case, this graph is modeling a power network where nodes are provide energy or consume energy, and arcs are transmission lines. Usually in the network reliability studies, failures in elements are assumed to fail independently. This network was exposed to synthetic earthquakes with data from the north of Chile, and we analyze how often the elements fail. So you can see in the left side of the slide, this is the relative difference between the probability that two elements fail simultaneously, two arcs fail simultaneously due to the earthquake, and the probability that they will fail if we assume they fail independently. So with the same earthquake, you compute the marginal probability that each element will fail, and you make the product to estimate the probability they will fail simultaneously. The problem is that for some pairs of elements, the probability of a simultaneous failure of two transmission elements exposed to an earthquake can be up to 15 times higher than a probability of a simultaneous failure, assuming that that they behave independently. So disregarding correlation and for us probably the dependence of the probability model that governed the failures, it changed absolutely the behavior of the model, and this will change the optimal network design and will increase the actual demand that is not satisfied. This is the curtailed demand. Okay, so we will think that we are designing with a certain level of security, but in practice we are attaining less reliability in this network. So we did another study for ice storm. This is another small network in the south of Chile. This is actually a network. This is near Concepcion. And we obtained a similar behavior. You can see that here we put the number of times that the simultaneous failure probability occurs versus the independent model. So here you see that sometimes 12 times and 10 times. So that you're incurring in a lot of error. Yeah. So to explain in simple words what kind of errors we will have if we assume independence, is this will lead us to buy the wrong insurance. So to assess risk, we buy insurance, and it's like that you decide to buy, instead of insuring your house, you're insuring your doghouse. So so you're putting the money in the wrong insurance. That is the effect that could appear if we don't use the correct model. Okay. So for simplicity, because or for reasons that it's make more treatable the problem, or more computational, more affordable, many times in the network reliability problem, people have assumed independence. And at the beginning, it wasn't about assumption, because many elements of the network fail due to its own, they become old, and this wasn't related to another element. But as network became geographically extended, and we rely more in networks, these other failures, like provoked by extreme weather events, become more relevant, and they are need to be modeled. Okay, and this independence assumptions becomes it becomes short to represent these problems. That is from the side of probability. From the other side, we have that network designers have today are designing the networks using the security criteria N-1. Yeah, this means that this is for electrical network and for communication network. And this means that the network should continue to provide the service even if one component have failed. Okay. This in the literature, trying to in the research literature, trying to provide more accurate models, but with some simplifications, they have assumed this independent failure assumption. But still, in both cases, we have that simultaneous failure of two or more elements are dismissed. Okay. When there is independent failure assumption, the probability that two elements fail will be very low compared to one element. And in the N-1 criteria, they assume it's impossible that they will fail simultaneously. Okay, so what we propose is use better models, and we can, for one side, we can bring probabilistic seismic hazard analysis, for example, that modulate directly the earthquake. From another, and we have also explored this area. And from another side, from the more theoretical side, we can use the Marshall-Olkin model. That is a model that captures correlation. So now I will explain you a little bit of the definition of reliability, and then I will move to the Marshall-Olkin model. Okay. So I will give just one definition of network reliability. There are a lot. This word is also related to the word resilience. That's more modern. And we will show you a very simple model, but this is a big area that can be very complex in more and more detailed definitions. Okay. So the reliability is defined as the ability of an item to perform a required function under a given environmental and operational condition for a state period of time. Okay, this is not. This is important because many times infrastructures fulfill different functions. So sometimes we could think that they are functioning for something, but not functioning for another function. For example, we could have that the internet will be functional if we want to send an email, but not functioning if we want to make a WhatsApp call. Okay, so it's important to define well the function. In a network, we will think that we have many components, that these components have two possible states, working or not. Okay, and they are these components are connected, and if some of them are working in this configuration as they are connected, we will say that the network is functioning. Okay? We will call the structural function the function that relate the vector of a state of each component with the state of the network. Okay. So this is just a function that goes from 0, 1 to the power number of component of the network to 0, 1. So given the state of the components, we obtain the state of the network. For example, the ST reliability, we will relate the connectivity between these two black dots that are here. And for this configuration here, we have that the two black dots are connected. Here we have the same because we have a path. Okay, here we have a path as well, in the third, but in the fourth and fifth configurations, you see that we don't have a path between the two black dots. So the first three, we say that they are connected, and the two last are not connected. The ST reliability will be the probability that the two black dots are connected. Okay, and this is the ST reliability. There are other measures of connectivity. So we could ask, for example, that the path should be no longer than certain size, or instead of connecting only two dots, two nodes, we would like to connect a subset or other things. Okay. The complexity is the problem is that already computing the reliability of a graph, it's an NP-complete problem. Okay, so if you are designing and you are choosing over a great amount of designs, you have a very big and complicated problem. That's why this kind of assumption like independence has been done to consider the problem, okay, to solve the problem. Okay, so here we have the same idea I was explaining before, that we have two states for each component. Okay, this is element. We will consider only the edges. Edges could be working or not working. Okay, at a certain time t. So for at time t, we have a state vector of the system. Okay, and the structural function will relate the state of the system to the state of the network. Okay, and we will have the probability that this structural function evaluated in the state of the system at time t is equal to 1 is the probability that at time t the system is working. Okay, so in the example I show you, the structural function is the connectivity between the two black dots. Okay. So now this structural function is a very nice mathematical element because it's allow us to separate the configuration of the network, so how components are related one to each other to make the network work, with the life of the components. And we will now introduce the model, the Marshall-Olkin model, that will tell us which will be the life of a component. We will assume that components are non-repairable. Okay. And the good characteristic of the Marshall-Olkin is that allow us to model a correlation. Okay. So the Marshall-Olkin lifetime model. It was introduced in 1967 for two variables, and it's very simple to explain. So consider that three exponential random variables, okay, with a rate lambda 1, lambda 2, and lambda 1, 2. So each of these exponentials times are related to element 1, element 2, and this is related to element 1 and 2. You can consider that these are like shocks that will occur at time given by the exponential time and will affect the variables in the subset in the subscript. Okay, and the life of component 1 will be the first time a shock affects component 1. That will be the minimum between time zeta 1 and time zeta 1, 2. Okay, and so the first time a shock hits component 1, then component 1 will die and will remain non-operative. Okay, so and the trick here is that the minimum between two exponentials, this is something you learn in your first course of probability, the minimum of two exponential behaves also as an exponential with parameters the sum of the two rates. Okay, similar to the other component T2. Okay, will have the same. So this allows us that all components' life will be exponential, and they will show dependence. Even more, they will fail simultaneously if the first shock to occur is the one that affects the two components at the same time. This very simple model can be generalized to an arbitrary number of components. Okay, so we will have variable zeta v that affects this zeta v. So zeta v will be the time where a shock that affects all components involved in the set v. And if they were already turned off, they will remain off. And if some component in V was still working, they will be turned off. Okay. In this way, we will have that the life of component E, T sub E, the life of component E, will be this component will remain working until the first shock hits the component. And this will be the minimum of all these exponential variables such that set V contains component E. So this is this worthy part that is in the minimum. Just think of this part to say, consider all set V such that V contains E, okay? And as before, this is an exponential random variable because the minimum of exponential random variables that are independent continues to be exponential, given by the sum of all the rates of the exponentials involved in this minimum, okay? So this is a very nice model. This has this exponential property. Marshall-Olkin inherits the memory loss of the exponentials and is actually the only multivariate model that has the exponential memory loss. So you cannot have a model more general than this one or with more parameters than this one that will have also the memory loss property. To relate to what we had before, the state of the component at time t, okay, will be 1 if the lifetime of the component is the time at this component will turn off is after instant t, small t. Okay, so this allows us to take a photograph at time t of how the components are behaving. Okay, so Marshall-Olkin is as I told you, it's the only multivariate model where life of each component is an exponential and it keeps the memories property. The Marshall-Olkin multivariate distribution is paired with the Marshall-Olkin copula by the survivor copula of the Sklar theorem and is one valuable model of extreme value copula. This is something that allows to model dependence. In large dimension, the Marshall-Olkin is a very flexible. We can capture a lot of settings, but it's difficult to work with because it has too many parameters. It had one parameter for each shock, and we have as many shock as subsets of elements. So we have 2 to the power number of elements, more or less, parameters. But this can be overcome, okay? This exponential structure, this underlying exponential structure that has the Marshall-Olkin allow us to make simulations, rare event simulations. It can be integrated in a stochastic optimization models to do network design, and under some assumptions, it is possible to estimate the parameters to capture this dependence. Yeah, the major drawback of the Marshall-Olkin is that cannot capture negative correlations. Okay, but in reliability, we generally see more positive correlations and very mild negative correlations. So this is, if it is a drawback, it's not that complicated. You can think what Marshall-Olkin does is, if we consider the same model that we were looking at before of the connectivity between the 2 black dots, we can consider like a Markov, a continuous time Markov chain. Each node will be a configuration of the network, and as component dies, okay, we will go changing from one configuration to another. The black arrows show what would happen if there was an independent assumption. In that case, components will die isolated, okay? And this one will be, each of these will be an exponential time. Adding these shocks allows to allow these red arrows that will make us skip some states like this one, and seeing and we will see that there will appear simultaneous failure. Like here, we have these two new failures, okay? And the red and the pink zone are all the fail state of the network, and the green zone are all the working state of the network, okay? So we can see that is walking. We have the like a walk with only one direction from the working state to the non-working state of the network. Okay, have just maybe a couple of minutes. We can estimate the parameters. I will skip a little bit here. We did our work with these networks. We use as a benchmark earthquakes, and the methodology we use is optimization problem to compute the shocks parameters here. And we will show you here what we did is we to do not have as many shocks. We started with shocks that can affect only one component. Afterwards could be affect one or two components, then could affect up to 4 components, that could affect up to 8 components, and up to 16. So we will have more and more parameters to estimate. And what you see here is that the error in the reliability computation, it's become a lot smaller. So here is if we have independence assumptions, it's a big error, and here we have a very small error. Okay, so it works, and it captures geographical correlations. And I will show you a couple of slides more. So the Levy-Frawlty. The Levy-Frawlty is a subfamily of the Marshall-Olkin, but can be constructed from scratch from a new idea. You will have a stochastic process that is monotone and increasing, okay? And this is the a Levy subordinator, but what you need to have in mind is just it's a random process that is increasing. And you have triggers. Triggers are here, like this. So each time the stochastic process, and the important thing is this stochastic process jumps and cross one of the trigger lines, this one, this will define the instant where components will fail, okay? And as it jumps, it will cross 2 or more triggers at the same time, making fail components simultaneously, okay? When this is, as I told you, a Levy subordinator, the process in blue, and triggers are exponential ID, we have the Levy-Frawlty Marshall-Olkin. This is a subfamily in the case where all components will have the same life distribution, and they will, and these structures is very interesting because it allows us to understand better the general Marshall-Olkin and to generate more efficient simulations, okay? So I will stop here. We'll maybe go to the conclusions. Okay. Okay. So just a few words. Marshall-Olkin can capture geographical correlation and has a lot of great properties to make simulations, to make computations, and have subfamilies that allow us to look at the general process and obtain more insight about this great tool that could be very useful to make the design of the networks that we will need in the coming future. That will be my talk. Thank you very much.
Thank you, Javiera, for the lecture. If someone has a question in the YouTube channel, is now. But in the middle, I have a question. That's when you, Javiera, when you explain about the Marshall-Olkin model, you said you used the z variables, z1 in the beginning, z1, z2, and z12. And you said they variables distribute like exponential variables, but they are independent variables. But I think I don't know, I didn't understand the z12, because the component 1 and 2, they are not independent, or how this compound, you know?
Yes, understand the question. So if we have two components, imagine, I don't know, this cell phone and this necklace, two components of a system, we will have, and we have three shocks. So the one shock could affect only this component. The other shock could affect only the phone. The third shock, that's zeta 1, 2, when it occurs, it affects both. They take off both components at the same time.
Okay.
So when we simulate, if zeta 1, 2 is the smallest of the exponential variable, they will come off simultaneously. You can think that this component will fail due to, because it became old, maybe, or something inside. This will be reflected by zeta 1. And this also could fail for some reason inside of it, and will fail because of zeta 2. But there could be an earthquake that could make both fail simultaneously.
Okay.
And that will be zeta 1, 2.
Okay.
Okay, that is the interpretation. So the life of this component will be the minimum of these two things: the probability, the lifetime that it fails on its own, or if an earthquake come and hit them both.
Okay. Thank you so much.
Mm-hmm.
And we are without question in the YouTube channel. So now we have the next transmission is the communication. So invite you to watch the communication. And thank you so much, Javiera, for be here with us.
Okay, thank you, Alejandra. Anytime, I'm glad. Better in person.
Okay.
See you.